Sure. Sure. Can you start? Can you hear me on the live stream? Okay, perfect. So hello everyone. Welcome back to this lectures on computer architecture related to memory-centric computing. So today I'm going to be your lecturer. I'm Geraldo. I'm a postdoc here, the Safari Research Group. I've been doing research on this topic for around 8 years already, almost 10. So I'm going to elaborate on some of the adoption issues that this type of architectures have presented itself towards. So in the beginning, I'm just going to give a little bit of reminder of what was lectured yesterday. So what Mohammed presented and what Onur presented last week. So that's going to be very fast, and then we are going to get actually to the system adoption problems related to processing in memory. So if you recall, the problem that we are trying to solve over here in general is that computing today is bottlenecked by data, and all applications are more and more data driven. We see this in application specific domains like the deep neural networks or genomic analysis, but this is a general trend regardless of the application domain itself. The main problem that this generates is that we are not designing systems to efficiently move data. So you as a designer is not much concerned about efficiency on moving data. That's actually, we design the system around to avoid moving, actually to just do computation and not centered on memory itself. This creates performance and energy bottlenecks in the system. This is exacerbated by the way that we design system, where we separate computation, communication, and memory and storage in different boxes, and then we individually optimize each one of those boxes. And right now we are very good at optimizing them individually, but once they interact with each other, this create this performance and energy bottlenecks that we are seeing for these applications. Onur also mentioned that if you look at real data for real systems, we see that even in small laptops. So this work was done in Chromebooks, which are laptops that are even weaker than what you're using right now. You see that data movement dominates system energy, and also for specialized machine learning accelerators, depending on the neural network model that we use. So the way to solve, one way of solving this data movement bottleneck problem is by doing computation where the data resides. So to make memory and computation, and also at some degree communication optimized together. So today we are going to go through those some of those questions that we posed before in previous lectures on how to design such systems. This idea of designing computation and memory together is not new. It has initially been proposed around the 70s and the seminar works. But right now in the current literature, this idea has been quite widespread, and we actually classifying those architectures into two different realms, depending on actually how you are integrating computation around the memory itself. So the first one is what we call processing near memory architectures, where you're going to add logic near the memory array for computation. And the second one is called processing using memory architectures, which use the operation properties of memory cells themselves to perform computation. And since this lecture today is more focused on adoption issues, you're going to see that depending on what you do, depending on near or using memory, different adoption issues are going to arrive. For example, in processing using memory, data mapping and allocation dictates where computation is going to be executed, because the data is stored in a place, and then in that same place, computation is going to be performed. So you're going to see later on that you need to actually co-design those elements together so that you can maximize utilization of resources for the processing using memory array. While processing near memory architectures are more forgiving, because since you still have computation and logic designed separately, you can map and schedule computation in a more flexible way. We are going to see all of that later on today in this lecture. In this previous lectures, we also mentioned that even though this idea is quite old, process memory architectures are right now being commercialized. So there are many manufacturers and also startups working on deployment those processing memory architectures to accelerate various workloads. So there were examples from Samsung, from 3D stack-based memory that use HBM or HMC, for example. While processing using memory architectures uses these analog operating principles of memory, for example, DRAM, to do simple operations. We saw in lecture that, for example, we can copy one source of one row of data to a different row of data inside a DRAM subarray by issuing back-to-back activations to the DRAM chip itself. So the first activation latches the data into the local row buffer of the DRAM array, while the second activation actually copies that latched data to the destination row. In this approach that we call row clone. This is quite inexpensive because you are just operating the DRAM chips in a different way. You are not modifying the DRAM array for computation itself. You also saw that if you can extrapolate this idea of consecutive multiple row activations, you can do in DRAM and NOR operations by activating 3 DRAM rows at the same time. This is possible because of this sense amplifier in the DRAM chip operates as a differential circuit that calculates the majority of 3 of the activated rows. So we saw that by controlling one of the activated rows, you can either perform OR operation or AND operation inside the DRAM chip as well. And again, this does not require modifications to the DRAM array itself. You can do modifications to the peripheral to make this more efficient, but it's not necessarily a prerequisite for this to actually work. So that was called embed. And we saw as well that we can, and we are going to come back on this later on, that we can compose sequence of in-DRAM row copy operations and majority of 3 and NOT operations to implement more complex arithmetic operations inside the DRAM chip itself. Using this SIM-DRAM framework. I'm going to come back to that, so I'm not going to spend much time over here. And we can further improve the execution model by segmenting the DRAM subarray in different areas called DRAM mats, so that we can implement a more high throughput, multiple instruction, multiple data execution engine inside the DRAM chip itself in MIM-DRAM. So this is just an overview of MIM-DRAM. Again, just to highlight. Over there, we just segment the DRAM subarray into those different mats where we activate only the mats that have data to do the triple row activation for the target arithmetic operation, hence improving SIM utilization. And in the unused portions of the DRAM subarray, we can implement different operations in a multiple instruction, multiple data manner. We can also leverage the peripherals of the DRAM subarray itself to move columns of data from one DRAM mat to another, and also to port code, vectorizable code into different columns of the DRAM subarray. I'm going to also come back to this later on during this talk, so I'm not going to elaborate much right now. Also, we mentioned in previous lectures that DRAM chips are already capable of performing these operations. We have a lot of studies using commodity off-the-shelf DRAM chips using FPGA-based platforms that allow us to have more fine-grained control of DRAM commands, and we see that we can implement those Boolean operations inside the DRAM chip with some high success rate. So all of this is very good and it's very nice, but why you're not having those systems in your pocket right now, right? Why they are not still deployed at large scale? And this comes not, there's an aspect of that which is business related aspects, generating or manufacturing these chips is still quite challenged business wide, because you have a memory manufacturer that does memory, and you have like Samsung or SK Hynix or Micron, and you have a processor manufacturer that does processing, Intel, AMD, for example. So if you want to design a memory that does compute, who actually is going to manufacture that, right? Should be SK Hynix, Samsung, or should be Intel, AMD, right? So ideally they cooperate and they manufacture something together, but that requires collaboration across different companies that have their own interests. So that is this business aspect related to adoption of process memory, but we are not much interested on those over here. We are more interested on the engineering aspect. So why engineering wise is hard to add those intelligent memories in current systems today. So this is what we are going to try to illustrate here in this lecture. So you already saw this before. In order for you to have application, your, I don't know, Chrome or email browser or email server, for example, executing your memory, you need to create a path, right, from the application to the hardware itself. And generating this path does not exist, right? You don't have a memory that does compute right now in your processor. So creating this path require us to have a holistic view of a system itself. So you need to first understand what are the properties of the application, of what are the portions of application or a function or a kernel or instruction that might benefit from process memory, because this is not a complete, this type of architectures are not a complete replacement for such for current systems. So you're not proposing to take your M1 or MX processor from your Apple computer, just trash it and just use memory. That's not the case. There are limitations to process memory systems that need to be taken into account for you to have efficiency overall for your system. So you need to understand those limitations, understand what those applications require, and what the system, the process memory system, is good to do, and map those applications to the hardware itself. Then comes the problem of programmability. Now that I identify which portion of my application or my function would benefit from the systems, how do I need to write code, assembly code, C code, high-level APIs, instructions to do that computation, that task that I need to be done inside the memory itself. So once that code is generated, how I actually manage that code running the system, right? That creates a bunch of system integration issues related to data coherence, data synchronization, virtual memory isolation, and communication interface, and many other problems that you're going to see here today. Once those problems are tackled, how we can provide runtime support to make the most efficient use of the hardware itself. And finally, as a researcher or as an engineer, how can you assess the feasibility of this type of architectures for your target application? So all of this requires to be addressed before we actually enable process memory at large scale. But most important is that we need to shift our mindset towards memory-centric computing instead of processor-centric computing. So this is the most important, and this is quite difficult because of the way that computer architecture is teach over the computer science or computer engineering curriculum. So a lot of engineers have just a processor view of memory, and memory is just a side note or some lectures that are taught in the end of the semester, and then you learn about caches or you learn about virtual memory, but you spend the majority of your studies actually learning about how to design out of order core or a GPU, for example. And this is okay, this is very important as well. But if you don't start thinking about memory more, of course, once you have many different options that you can use to actually design a new generation system, you're going to think about what you know, right? And what you have been working over the years. And I think this is one of the main advantages of this particular curriculum compared to others, because we start from the beginning having this a fresh view on computer architecture in a more memory-centric way. So, of course, during the semester, you're also going to look at processor-based optimizations and how you can design better processors. But you already have, hopefully, after those 3 lectures, an idea that data is a problem, and you might have tools to solve this problem other than using processor-centric designs. So let's start then revisiting the computer architecture stack and going one problem at a time. I start with application and software support for processing memory. So let's say that you have this new pin system and you have a new application, and you want to see if this application might benefit from this pin system. So intuitively, what would you look at application to try to see if it's going to be beneficial the system or not? Is any hints? It's quite straightforward, actually. Been talking about this for the last 15 minutes. What is the main key metric that would you look at in the application to see if it would benefit from processing memory? Any data movement, right? But how you quantify data movement is quite arbitrary right now, right? It's quite abstract. So I don't know if you ever were using your laptop and then everything start to go a bit slower and your fan start going crazy and your computer start overheating. Usually that is an indication that there is a lot of memory traffic in your system. But as well, like just looking at the speed of your fan of your computer is also not the best metric, right? So there are tools and there are approaches over there to try to actually characterize data movement, to give a number and tell us based on this number if this application is more memory intensive or more compute intensive. So if you are into GPU programming or programming for deep learning, you might have came across this model called a roofline model that is quite commonly used to classify if a layer of a network, a neural network, for example, is more memory or compute bound and would require you to optimize, I don't know, the size of your caches or optimize the code itself. So I'm going to briefly explain how this model works. This is not necessarily just related to process memory. This is related to application profiling as a concept. So we have this very simple model, this plot, that in the x-axis we have the arithmetic intensity of a given function or application. And this is calculated based on the number of arithmetic operations that you do per bytes that you access. So let's say that you have a for loop that you load, you're doing a vector addition or addition operation. So you load 2 scalar operands, a plus b. Each one of them is, I don't know, 32 bits, 4 bytes. So you're loading 8 bytes. You're doing one operation, which is the addition operation. So 1, and you store 1 byte as a 4 bytes as the output. So I'm just doing C equals to A plus B. So the arithmetic intensity for that particular sequence of instructions would be 4 times 3, so 12 divided by 1 addition that I'm doing. So this is just give you an indication on how much compute I'm going to actually need for that particular piece of code. And then in the y-axis here, we have performance. This is actually measure. So how many giga operations per second I'm achieving for that particular kernel or loop. Then we have 2 main roofs that are dependent on the system that you have. So the first one is this horizontal line here, which is called the compute roof, which is defined by the peak system throughput of your application, of your system itself. So let's say that you have a processor that has 1 arithmetic unit that does 1 scalar operands every cycle, and that cycle is 1 nanosecond or like 1 gigahertz. So the peak throughput of that is that peak throughput of that particular arithmetic unit, right? So it's going to be one operation every 1 nanosecond. Of course, if you have more arithmetic units, that's going to be multiplied by the number of arithmetic units that you have. Then you have this other roof here, which is we call memory roof, which is equals to the the bandwidth of your memory. So in DDR4, for example, one channel of the RAM gives you 19.2 gigabytes per second. So that will be that bandwidth multiplied by the arithmetic intensity of the application itself. So this gives you basically how much memory that particular application is consuming. So that is the model. And then people classify the applications as points in this plot over here. And if a point lies below the compute roof, you tell that this application is compute bound because you are loading a lot of data and you are utilizing, you're not loading a lot of data. You have a lot of operations operating over few amounts of data. So you're actually going to be bound by the number of operations that you can do in a cycle. So that output of the arithmetic unit. But if the point lies below the memory roof, it means that you have lower arithmetic intensity. So you're loading a lot of data, but you're operating, you're doing few arithmetic operations of that loaded data. A good example is just this simple addition that I just mentioned, C equals to A plus B. You're loading 12 bytes, but you're just doing one operation over those 12 bytes. And then in that case, you're going to be bound by how much faster you can load the data itself. And then we call those applications or functions memory bound. And now we have a way of classifying data movement, right? And then we can say if application is memory bound, it's going to be the data movement is going to be high, so it's going to be suitable for processing memory. While if the application is non-memory bound, it's going to be compute bound, it's not necessarily going to be suitable for processing memory. So let's see how this model works when you actually plug many applications over here. So we run these experiments over more than 100 applications for different domains, and we classify based on simulation those points into 4 main categories. So applications that are faster on the CPU than on the NDP system, applications that are faster on the pin system compared to the CPU, applications that have similar performance independent on the system, and applications where the performance is going to depend on the particular system configuration. For example, the number of cores that are available in your system. An important note to give is that this roofline model is not necessarily is not a model that is designed to process memory. It's not a model that has process memory in mind. It's just a way of classifying data movement and memory intensity of a system. So let's see how this model works or how this model performs when you actually trying to plug this model for pin suitability. So as expected, we have some applications here that are memory bound, so they are below the memory roof and runs faster on the pin system. So the model is behaving very well. So data intensive applications benefit from processing memory. And then we have some applications here that are compute bound and not necessarily benefit from process memory. They run faster on the regular CPU, which is as expected as well. However, we have a bunch of cluster of applications here, for example, applications that are memory bound that not necessarily benefit from processing memory, which is very weird, right? Because we are saying for a long time that memory bound applications benefit from process memory. And at the same time, we have applications that are compute bound and benefit from process memory, which is also not expected from this model. So the conclusion that we have here is that this model in particular, this roofline model, cannot accurately account for process memory suitability. Why is that? Because this model is very simple. This model is just using a metric, arithmetic intensity, to try to indicate if you're going to load a lot of data or if you're going to do a lot of compute. But there is no aspect of more complex things in this model. For example, how fast or how often I load the data, or how far away is one piece of data from another, and all of those aspects are going to impact process memory suitability or not. Is there a question? Sorry, I told you to raise your hand. Okay. So let's look at another way of classifying data movement. Let's look at there is this other metric called less level cache misses per kilo instructions. So LLC misses per kilo instructions. So what is this? So you have your cache hierarchy in your system, L1, L2, L3, and then after your L3 you have DRAM. So basically here you calculate how many misses you have in your L3, and you divide the number of misses by the 1,000 every 1,000 instructions that you have. So every 1,000 instructions, how many misses I have? So sorry, if I have a high number of misses in my less level cache, level cache, every 1,000 instructions it means that most of my instructions are actually just servicing memory. So memory bound by definition. And people have drawn different threshold values for this metric to say if application is memory bound or compute bound. And the same rationality apply here. If application is memory bound, it's going to benefit from PIM. If the application is not memory bound, it's not going to benefit from PIM based on this particular definition of memory bound. So let's look at how this model apply. So here we have applications that have high less level misses per kilo instruction, and they benefit from PIM. So this is good. We also have applications with low less misses per kilo instructions, and they don't benefit from PIM. They run faster on the CPU. So that's also good. However, there are a bunch of applications here that have low less misses per kilo instructions, but they don't benefit from PIM, or they benefit from PIM, or the performance depends on the system configuration. So basically, there is a lot of nuance over here that this model, again, is not capturing. So again, using a simple metric is not enough to indicate process memory suitability. So to try to solve this issue, we develop a methodology that is going to combine different metrics to try to give more insight about the data intensiveness of a particular application running in a system. And based on that, try to indicate if process memory is good or not. So let's look at how this framework or this methodology works. So first, we take the application and we do some profiling in the application. This step is completely optional, just to see which region of application is taking the most amount of time, because we want to optimize that particular function, right? Rather than optimizing the portion of the application that's not taking much time. Then we use some simulator that we developed to collect memory traces of application, and then based on this memory trace, we classify the locality of the application, so the spatial and temporal locality, and that's going to be more concrete next. Also, we run some simulations, and we do what we call scalability analysis, where we classify the memory bottleneck of the application into using, again, system-related metrics. Then, based on the data that we collect from those two steps, we classify the application into 6 different classes of data movement bottlenecks, and each class of data movement bottleneck either can indicate if the application is going to benefit from PIM or not. So let's look at those steps in more detail. So the first step, as I mentioned, is just to try to identify functions in the application that takes a lot of time and are potentially memory bound. Then the interesting part arrives, where we actually are going to start calculating application-dependent metrics, those being spatial and temporal locality. So is there anyone that have an intuition why spatial and temporal locality are important metrics over here for classifying data intensiveness of application? So if you have low spatial locality, for example, in your application, what's going to happen in your caches? Exactly, you have more misses. Like the entire premises of caches of your CRAM caches is that you want to capture locality in the application, right? So you always have this intuition of caches that if you want to go to the library, people don't go to libraries that often anymore to pick up books. But if you want to have a snack, for example, in your room, you just bring whatever snack from your kitchen that you're going to consume earlier. So it's already there, right? So you don't have to go to the fridge every single time to get the snack. So that's the entire premises of cache, is reuse and locality. And if you don't have this reuse and this locality, you're going to end up going a lot of times to your main memory. And this is generating that data movement bottleneck that we have been talking about over here. So the first type of locality is spatial locality, which tells you how if I bring one particular cache line. So usually when you access data in DRAM in cache line granularity, so you don't access individual scalar values. So a cache line is around 64 bytes. So if you have an array with scalar values, for example, that are 4 bytes, you bring 64 divided by 4 elements at once. So you don't have to pay for the trip all the time. So this is important because if you have enough spatial locality, means that you are accessing elements consecutively, one after the other. So you are hitting in that cache line that you brought from the main memory quite often. So this is good for your processor, not necessarily good for process memory. So there is a way of classifying or to calculating spatial locality in the application using what we call stride profiling histograms. So basically, so if you get the memory trace of our application, and then you look at a particular memory access and the next ones in a window. And then if the follow-up access in that window is 1, so in this case here, you're always accessing the next element in this array, you increment that bin with the particular position 1 one time. If you would access element 0 and then access element 2 and then access element 4, then your stride profile would be 2, and then you would increment the bin 2 over here, and so on and so forth. So after that, you can do the common distribution of these histograms here and normalize that to a value between 0 and 1. 1 meaning that application have high spatial locality, and 0 meaning that application have a low spatial locality. The other metric is temporal locality. So here we are not much interested on how close the access are, but how often I access the same thing multiple times. So again, we use some histograms to calculate this metric, but now it's not a stride anymore, it's reuse. So every time that I'm accessing the same address, I increment that particular position in my histogram by 1. For example, here I'm accessing element A in an array 4 times. So I increment that position in my histogram by 1 for a particular window of accesses. Again, we can normalize this to a value between 0 and 1, meaning that if application have high temporal locality, the value is going to be 1, and low temporal locality is going to be 0. Can you think of application that have, for example, oops, let's go back. High spatial locality, but low temporal locality? Yeah, convolutions are a very good example. Because you are always accessing a window of, for example, a grid of 3 plus 3, so 9 access, so they are quite clustered. But once you move to that window, after you move away, you're not going to access that again, that particular portions of your matrix multiplication often. So that would actually give you to a high spatial locality, so elements are clustered together, but you don't keep accessing the same element once you move away from that convolution window. So it's a very good example. So intuitively, you can understand why something like a high application that does convolutions over a large amount of data would be memory intensive, right? Like attention, right? So this is why, for example, a lot of those pin systems that we saw before, are targeting generative AI in particular, because convolutions, depending on the size of the data, are becomes a suffer from low temporal locality. So caches are not that useful. Okay, is there any question related to those metrics? Okay, so those metrics gives you an intuition about the application itself. So it does not necessarily depend on the system. So temporal and spatial locality does not depend if you are going to run this application on your CPU processor, in your GPU, or in your accelerator. It's just a factor on how the code is written and how the code is accessing data. So it's a property of the application. But that's not enough, because you don't run the application in a void, right? You're going to run the application in a given system. So we use metrics that actually measure the system itself in the third step. Those metrics being arithmetic intensity. This is exactly the same metric that I mentioned in the roofline model that shows how compute intensive your application is. Then you're also going to use the last level misses per kilo instructions to show memory intensity. But you're also going to use a new metric called last to first miss ratio, or LFMR, which is defined by the number of last level cache misses by the number of L1 misses. So what this is showing is, if this metric is high, it means that I had a miss in my L1 cache. Then this miss in my L1 cache also was a miss in my L2 cache, which was also a miss in my L3 cache. So my caches are basically useless. And then you're going to see that this is a good indication for processing memory suitability as well. So based on all of this data, we create some model which you classify depending on if those metrics are high or low. And this low and high here depends, is like parameters of the model that we train over a large amount of data. And we classify those particular applications into 6 different classes of data movement bottlenecks. So those bottlenecks have something more classical, like if application is DRAM bandwidth or latency bound. So you can see here, for example, if your application have low temporal locality, your last to first miss ratio is low. If your MPKI is high and your arithmetic intensity is low, your application is going to be memory bound. But if all of this happens, but your misses per kilo instructions is low, your application is going to be latency bound, and so on and so forth. And each one of those classes of data movement bottlenecks correlates with different data movement mitigation mechanism. For example, if your application is DRAM latency bound, it's likely that it's not going to benefit from increasing the size of your cache hierarchy. While if your application is L1 or L2 cache capacity bound, increasing the size of the cache hierarchy is a way of mitigating the movement bottleneck at some extent. So you don't need to go to processing memory. While in those first two, you can increase the size of the caches as much as you want. It's not going to be enough. You're going to end up always being bound by the DRAM itself. Because again, there is no locality to be captured by the caches. So yeah, so this framework, this methodology is available online on your GitHub, and there are more on this on a longer lecture. So there is any question on this methodology to define data movements in application? So hopefully you learn a little bit about application profiling, which is quite important in general. It's just not related to process memory. It's a very important skill to have, to look at this memory, those metrics that I just mentioned, and try to have an intuition on based on those metrics if a particular system is going to be beneficial or not for that particular application. So okay, so all of those what I just mentioned in DAMOV is trying to tell you based on some metrics if application is going to benefit from a system or not, right? A different way of looking into this problem is by simply run an application in the system. Of course, that requires more engineering, right? Because now you have to sit down, write the code in the application for that particular system, execute and measure. And it's also assuming that you have access to the system itself, right, to run. So, and we have mentioned in the previous lecture that there are these commercial process memory systems called UpMem. So this UpMem architecture is a processing near memory system that adds some logic over here. So it adds some general purpose processor nearby DRAM banks in the 2D form factor. So this is the system itself. We have your regular DRAM in those slots in red. Then you have, DIMMs with this particular pin chips that has both DRAM and a RISC-like general purpose cores over there. Then you can do computation. So we had access to this system. We still have actually. And then we did exactly what I just mentioned. Now that we have the system, to see if application would benefit from process memory, I could just write code to this system, test the application, and see if this application is going to be run faster on the system or not compared to a CPU or GPU execution. This also enables you to do a profiling of the system itself and understand better its limitation. So to do all of this, we create this benchmark suite called Prim, which has 16 different applications from different domains, where we actually wrote the code and deploy on this UpMem pin system. After that, we keep designing more and more applications in this UpMem pin system to also to understand how good the system is for different domains. So this includes machine learning. We also implement optimizations for that particular system for these applications. Also, sparse matrix multiplication. Over here, translational functions, the sequence alignment, and homomorphic encryption, reinforcement learning, machine learning training. So the limit is, since this is a general purpose system, you can implement whatever you want and deploy there, test, and see if this application is going to be beneficial or not. And this is why I'm just skipping very fast over there, because it's just the takeaway that I want you to have over here is that another way of understanding if application would benefit from process memory is just by deploying that application in the system. But that requires you to invest in the system first, right? So it might be not the best first step. But it's a different way of handling this first application identification problem. So it's very close to the break time. So before I get to easing of the programmability, let's take a break and come back at 2:13. Let's continue. So I had a very good question during the break about spatial and temporal locality and processing using memory. The question is, doesn't we need locality to do processing using memory operations, like the ones that you operate inside the DRAM array and you do like in DRAM row copy or in DRAM majority operation, right? So the answer, yes, we need locality, but this is why you cannot just look at one metric individually, right? Because we need spatial locality because you're operating on vectors, and those vectors are the size of the DRAM row buffer. So, or if it's in BIM DRAM case, fractions of that, but it's still a fraction of the row buffer. So you definitely need spatial locality, but you don't necessarily need temporal locality, right? So once you feed the data inside the DRAM subarray and do the computation, there is not much of interest of the substrate if you're going to reuse the data or not, right? And often the case of the applications where processing using memory are quite good are those applications where we have very wide, so a large amount of spatial locality, very wide SIMD registers that you are operating over, and you don't access that SIMD registers many times. So it means that you have to have a lot of data organized in a spatial way, but you don't access that data of multiple times during the execution. So this is why, for example, a GPU, which also operates on SIMD-based programming, would not be a good substrate for those type of applications, because yes, you can have spatial locality to use the GPU caches at some extent, but since you're not reusing the data, you're going to end up causing data movement problems. So that was a very good question. Okay, so let's go to the next adoption issue, which is programmability. So many slides. Okay. So how you can program, now that you identify the application that's suitable for processing memory, how can you program the system itself, right? So we saw already in the previous lecture one simple way of doing or handling programmability issue with the pin-enable instruction applications, where we look at the application and we see that the application in this particular page rank, right? There's a simple instruction. So here, just an update of a scalar value over a lot of data. So here you're traversing a very large graph. So you need to keep moving data in and out of memory for just one instruction. So this is a very good example as well of low arithmetic intensity, which is one of the metrics of DAMOV, right? So here you have 65 bytes that you are having, that you bring in and out of the system, so 128 bytes in total, but you only operate over one element. So the arithmetic intensity here would be operations per byte. So one operation over 128 bytes, so very low. So we saw that we can offload this simple instruction to the DRAM chip itself, so that the DRAM chip does the update without moving the data in and out. You just move the output, the input or the output, depending on the type of the operation. So in that case, you're still doing one operation, but now you only have 8 bytes going around, which improves arithmetic intensity. So these have advantages and disadvantages. I'm not going to reiterate because it was already explained last lecture. The main disadvantage of this is that it does not take full potential of the system, because you're operating over single cache lines. This is one main problem, maybe because when you look at the internal bandwidth of the DRAM chip itself, since the way that you access data is in columns inside the DRAM chip, when you're doing access, if you're only accessing a scalar value, you are underutilized at bandwidth. So when you're accessing a column, which is around 64 bits, I don't think about this 8 byte here, you're going to be confused. But when you look at 64 bits of a column that you access, and you access, for example, 1 byte in that column for that particular instruction, and why is 1 byte over here? Because you have multiple the DRAM operates in lockstep. We have multiple chips, so for example, 8 chips, and then you access the column inside each one of those chips, so 65 bits in each column, and then each one of those chips, of those columns, contributes to portions of the data that you read. So in that case, each one of those 8 chips contributes to 1 byte. 8 chips type 1 byte, 8 bytes in total. So this is the math that I'm doing in my mind, but don't get confused about that. It's just the fact that the column is too large when you access the then you access a scalar value, and if you do instructions like this, you're going to not fully utilize that column. So basically, it's throughput wasted from your DRAM chip. This is why it's written here that you don't take full advantage of your pin architecture itself. So this is one important drawback of doing this type of single instruction pin execution. But anyway, so there are other ways of dealing with programmability. We mentioned also this other work, Tom, where we use a network of, you can think about those as simple GPUs integrated in the logic layer of a 3D stack chip. And then over there, we have some programmability support based on loop execution to distribute computation across this stack. But more important, we are going to look next on programmability of the up-mapping system, because it's a real processing memory architecture that you can deploy today. And you may or may not have a lab related to the up-mem programmability during the semester. I don't know exactly if it's going to be a lab this year, but in the previous year was a lab for this particular class. So it's important to know the challenge of programming the system. So, okay. So this is just, again, a picture of the up-mapping system. So here we have the whole CPU. I will have the main memory, so your regular DRAM chips. You have the pin-enabled memory, and inside the pin-enabled memory, we have the multiple of those DPUs, which constitute of some portions of DRAM bank, so 64 megabyte of DRAM bank, a DMA engine that is used to move data from the DRAM bank to a scratchpad memory called working RAM. This is SRAM. And then the pipeline of the processor access the working RAM here. So the pipeline does not directly access the RAM. So the access goes through this scratchpad memory over here in the SRAM. So you have thousands of those cores inside the entire system. So you have 8 per chip, and you have multiple chips per DIMM, per rank, and so on and so forth, and per channel. Another important thing is the programming model that this system operates over. So this might be very counterintuitive because you're talking about moving or reducing data movement for quite some time. But the way that this up-mapping system is designed is as a loosely coupled accelerator. What does it mean? It means that you have your main memory, which your processor is using, and you append that main memory with this pin-enabled memory for computation. But this pin-enabled memory cannot be used as the main memory of your processor. So you have now 2 areas of memory in your system that are disjoint. This is similar to GPUs, right? So if you ever program a GPU, it's exactly like that. So you have your DRAM, and then you have your GPU, and inside the GPU you have some main memory, like HBM chip, for example. And if you want to execute anything on the GPU, the first thing that you need to do is to copy the data across the many cores in the GPU. In this case here, the many cores of the pin chip. And then you need to move the data from the main memory to the pin-enabled memory before the computation. So this goes against what we are discussing so far, because you are creating more data movement, right? Why it works like this is because of system integration issues. It's much easier to loosely integrate accelerator in the system, because it's not the case here, but it's, you can just plug, for example, the accelerator in the PCI slot of your system. This is not plugged in a PCI slot. It's just is another type of interface. It's the same as a DIMM-based interface, but again, it simplifies system integration because you don't need to tightly design this system that is running together with the hardware itself. So this is mostly for portability. So, but the entire idea of this mapping system is that, and it's similar to GPUs, is that you're going to be able to amortize this data movement here once you start doing the computation. So hopefully you do this data movement once for copy input data, then you're going to process that input data, and that's going to generate a lot of temporary data that you're not going to move out of the system, and then you just copy the output. So hopefully what you do, the data in, out, plus out is smaller than the volume of temporary data that was generated when you're doing the computation. Then you need to manually handle the scratchpad memory inside the pin system itself. So as I mentioned, there is no direct communication between the pipeline and the DRAM bank. So you cannot just load and store data into the DRAM bank. Everything needs to go through this DMA engine. And all of the access are to the scratchpad memory. So you need, as a programmer, to manually handle these copies from this DRAM bank to the working RAM, and finally to access to the ILU itself. And finally, you need to copy back the data and consolidate results from the pin-enabled memory to the CPU and main memory. So these are the steps that you need to go through when you're programming this mapping system. And then we are going to see how this translates to code. So let's say that you want to implement a vector addition operation in this upmapping system. I'm going to highlight a bunch of code here. It's not very important for you to know exactly this code, because if you have that lab again this semester, there is a manual that explains each one of those in more detail. So here is just for you to have an idea on the amount of lines of code that needs to be written just to do something as a vector addition. So the first thing that you need to do as a programmer is that you have the data, and then you need to align the data in the boundaries of the DRAM bank. And in the particular system, the DRAM bank is 8-byte aligned. So you need to make sure that all of your input arrays are 8-byte aligned. Then you need to collect input parameter that is going to be copied back to the pin system, and distribute them using special APIs that the UpMem SDK provides. Then you launch manually the application that you need to do, and also specify the type of synchronization that you're going to have between your DPUs and your whole CPU. So it can be synchronous, so the CPU waits for the computation to finish, or it can be asynchronous, so it triggers an interrupt when it's done. Then you need to collect the output data from the DPUs to the back to the host memory, and note that everything again needs to be 8-byte aligned. You need to manually copy the data inside that scratchpad memory that I mentioned, the WRAM, and orchestrate the reads and write operations from that scratchpad memory before actually doing any arithmetic operation. So you need to do all of this. You need to write all of this code. It's much more than this. This is a simplified version. But in the end, the only thing that you need to write actually is vector addition. Like the only useful code that would actually require to write is these 4 lines of code over here. So all of this is to show that programming this type of system requires non-trivial effort. So you as a programmer need to understand the underlying hardware. So you need to understand alignment issues. You need to understand how different ways that the system needs to synchronize with the whole system. You need to understand that you need to orchestrate some 64 kilobytes of scratchpad memory inside each one of those DPUs. You need to manually move data from that DRAM bank into the WRAM. And this creates a programmability barrier for this mapping system. So with the work that I'm going to mention here, we are going to try to solve this issue using different ways. So the first way is to using APIs, and this will call Simple PIM. So what you're going to do here is you're going to provide 3 different high-level APIs. This is C++ code. So it's 3 classes in C++ to manage the pin system itself, or manage the data that this pin system is going to execute, communicate APIs to allow for the communication across the host and the pin, and also across the pin systems, the pin cores, and also some processing interface that dictates how data is going to be processed inside the pin system itself. So very briefly, let's look at these managed interfaces. So the first one, as I mentioned, it's just to register which piece of data is going to be stored inside the pin system. So, and it provides three main functions. So lookup, so retrieves information from an array that you registered before. And in the end, the free, for you to free an array that was registered as a pin resident array. So this is just because there is this separation between arrays that are going to be executing the host and arrays that are going to be executing the pin, and somehow you need to tell the system which one is which. So this is why this managed interface is doing. Then you have communication interface for host to CPU, pin to host to pin communication. So you can have an array, then you broadcast this array to make multiple copies of this array across different pin systems. So you copy the data across multiple pin systems using this broadcast API. You can also gather or scatter. So you have an array, and you scatter this array across different pin systems in an interleaving way. Or you can gather data from the different pin cores, and then you gather them in form into a single array back to the whole system using those APIs. Then you also have pin-to-pin communication APIs, where you can apply an operator on top of the communication. So, for example, you have multiple pin systems, and you might want to reduce a scalar value into a different scalar value. So here, basically, you're summing each one of the data in the arrays across different pin systems together. Or you can do an aggregation of an array that is in different pin systems into a single larger array in this all-gather communication. Then you can also process the data using those processing interface using what we call data parallel programming. So this is similar to another way of doing parallel programming called MapReduce, which is quite popular in Google as a Google programming framework that's quite popular over there. So basically, you either apply a map function to input different elements of an input array. The main thing here is that you are applying the same function over all of the elements of the array, generating an output array of the same size as the input array. I said array many times here, but basically is you have a for loop, and then you go element by element in this for loop one at a time, and you do the same operation in each one of the elements. Then you have a reduction. So we have basically a reduction function that specifies how you should aggregate different elements in an array to form output array of variable size. So this is why it's MapReduce. So you map the data or reduce the data into a smaller amount of data. And you can also combine different data in a zip function. So you have two arrays, and then you combine them into a single array of the same dimension of the initial two arrays. We also implement several code optimization in the back end. So this is a software API that generates the code automatically that I mentioned in the beginning here to the optimizing system. So now you have this differentiation between what's the front end being those APIs that I mentioned here, and the back end that actually takes this API codes and generate the codes to the mapping system. So you have opportunities to implement code optimizations such as strength reduction, loop rolling to reduce the number of control that you have, also bound checkings again to reduce the number of control function annealing to reduce function calls, and adjust transfer size depending on the optimization that is enabled. So we evaluate this framework using 6 different workloads from this PRIM benchmark suite that I mentioned earlier, and we evaluate it in a real mapping system with more than 2,400 pin cores. So just as a high level for you to understand how much code is reduced when you implement code for the PIM system using simple PIM. So this is an example of a code that does a histogram computation using the PIM SDK code. And this is not the entire code as well. You can see the dot here over here. And this is the code that I just mentioned before, right? So you need to initialize a bunch of variables, load data into the scratchpad memory, do bound tracker checking. The histogram calculation is not even here. But this is the same code using simple PIM, and now you just need to call the functions that does the computation for you. So you need to scatter the data across the PIM chips using the that scatter API. You run the histogram doing a reduction operation, and you need to do some iterations, of course, to handle the input data itself. So as you can see, this significantly reduced the number of lines of code to do the computation. And since we do those optimizations in the back end, we can comparable or high performance code compared to hand optimized code for both strong and weak scaling for those applications. And this is available online. So this is nice, but can you point a limitation of this framework? So you as a programmer want to think about how this data is actually moved, like from how you, if you reduce or if you gather or if you scatter or all of those data movement issues. So this I mentioned in the beginning, right? The main problem is that the user needs to have knowledge of the hardware. So this is not fully transparent, right? So the user still needs to understand that is a host and then there's a PIN system, and then that you need to move the data from the host, from the PIN system, and distribute and gather and scatter, all of those things, right? So this is not fully transparent from the user. The programmer still needs to have some control over here over the input data that it needs to operate. So hopefully that's clear. So let's see how we can fix that. So this is exactly what to try to do in the next work, DAPA. So we are going to rely more on this concept of data parallel programming to generate code for the upmapping system. And then we are going to have this framework that has three main components. I'm going to show here is much easier. The first component is a collection of data parallel pattern primitives. Again, this is not new. This is based on common skeletal-based programming for parallel programming. It's called common in multi-threaded systems, multi-core systems, or GPUs. And so in simple PIM, we have those three primitives, right? MapReduce and zip. And here we are going to extend those primitives to more primitives that allows you to implement more applications. So filtering, so you apply not prediction, I forgot the word, but you apply a function into the input data. And if that function is true, you have a copy of the data for the particular position, or if it's false, you don't have the copy of the data. Predicate over the input data. So you have a window, a rolling window type of function that you apply of the input data, or a non interleaving rolling window that you apply in the input data that's called a group. And you can also combine these different data parallel pattern primitives to do more complex operations. The thing that allows DAPA compared to simple PIM to remove that knowledge of data communication completely from the user is this concept of this data flow programming interface. So now the user is going to completely forget about PIM and is just going to focus on trying to rewrite the application in a way that data moves across stages of functions. So you're going to have each stage representing a different data parallel pattern, and then data is going to move from one state after the other. This is going to be more clear when I show the code example. And finally, similar to simple PIM, we are going to have this join of a front end to the back end. In the back end, you can implement optimizations when we are generating code to the UpMem PIN system, including doing computation together in the host and the PIN system at the same time. So let's see how this works. So let's say that you want to implement this vector reduction operation over here. Sorry, not vector, as a dot product operation. So the first thing that you need to do as a programmer is try to identify which parallel patterns you need to use to implement this application. So here we are going to have a map operation that's going to do the multiplication portion, and you're going to have a reduction operation, which is going to do the addition in the vector addition operation. So then you sit down to write your C++ code, and then the only thing that you need to do is specify the pipeline that does this computation. And the only thing that you do in the pipeline is, as I mentioned, a map. Then you specify the input data, and then you do multiplication over there, and a reduction operation from the output of that map. And then you do the reduction in the sum value over here. So note that compared to simple PIM, or even compared to UpMem, there is nothing related to PIM here, right? This is just a different way of writing parallel programming code to decoupling that vector.pod operation. Then we are going to have what we call a dynamic templates-based compilation, which is going to look at this data flow programming interface that the user wrote, and it's going to identify which are the input arrays that needs to be executed in the PIN system, distribute these input arrays accordingly to the different PIN units, and then, of course, handle that scratchpad memory and everything, alignment and all of those problems, and trigger the computation one stage at the time. So this is way more transparent related to the PIN system than simple PIN, for example. So the back end here could be any PIN system. So here we're using the UpMem system as a case study, but the code itself does not give any indication of the PIN system that you're going to have. So it means that you could implement different back ends targeting different PIN systems for the same front end code that was generated by the programmer. So again, we implement this and test in a real UpMem PIN system. And as you can see, we can improve performance based on those back-end optimizations that I mentioned earlier compared to the hand-optimized code. And we can significantly reduce code compared to hand-optimized implementations. So, and as I mentioned, compared to simple PIM, we have a higher abstraction level because the user does not need to specify communication patterns for the code itself. We support more parallel patterns and further optimizations. Okay. So this is a different way of doing programming substrates for process memory programmability. Is there any question related to any of those? Okay, so let's look at another way, which is in Memory-DRAM. So another way is to actually implement a compiler. So all of these works will not implement a compiler itself. It's just frameworks that the user still needs to compile the codes to the UpMem PIN system. But here we are going to actually get a compiler, in this case is LLVM, and you're going to modify the compiler to generate code for, in this case, Memory-DRAM, which is a process using DRAM architecture. Have anyone here taken a compiler class before? No. So what I'm going to say next is going to make no sense. But anyway, basically, just as a reminder, what we need to do in Memory-DRAM is to identify SIMD code, so single instruction multiple data code that is going to feed. We are going to feed into the DRAM subarray to do the computation, right? In model compilers, so model processors in your computer, for example, have what we call vector engines to do. Traditionally, they were proposed for multimedia operations in the past. They were called Intel processors. They were called MVX, if I'm not mistaken. And then they moved to more general general vector code over the years, and now in Intel processors we have what's called AVX instructions. So they have two series. AVX, there are three series: AVX, AVF2, and AVX 512. And these change based on the number of lanes of from the number of scalar operands that you can do at a given time for the vector instruction. So one way of taking advantage of that engine in your processor is not only Intel, your M1 based on probably ARM. I also have one coprocessor called Neon that does vector code. One way to leverage those instructions is to sit down yourself and write code that does vector instructions, but that is very tedious. So usually people just do that for highly optimized code. Another way is to, when you compile your application or operating system or whatever, the compiler tries to identify loops in the application that have are regular enough and can be vectorizable to that particular coprocessor. So those Intel or Neon processor in your system. So this is what is not related to PIM, but it's a good thing for you to understand. So it makes a little bit of sense of what I'm going to tell next. So this engine already exists in model processors. So in GCC, you have an auto vectorization engine. You can compile, you can control the vectorization with some flags in GCC when you're compiling an application. If you compile with O3, for example, it automatically tries to vectorize as much as possible. And it's the same for CLang, which is a LLVM open source based compiler. So we are going to take advantage of that auto vectorization engine that already exists in LLVM, and instead of generating code for this AVX coprocessor or Neon coprocessor, we are going to generate code for our Processing-in-DRAM substrate. And what is the main difference? So the main difference are twofold. So first, the number of SIMD lanes in model processors are quite limited. So you have in AVX 512 SIMD lanes. And if you just try to fully utilize those SIMD lanes, often you create problems like there is this problem called register spilling. So you're keeping loading data into register values, vector registers, loading them into the SIMD unit and trashing back. So this keep going back and forth. And this reduces the throughput of the vector processor itself. So there is a cost model in the processor to try to understand if it's better, depending on the target SIMD utilization or the target vector length of the particular loop, if it's better to just use that code as a vector code, or if it's better to use it as a scalar-based code so you don't run into those register spilling problems that I just mentioned. So there is a cost model there based on that size because of the limited size of the vector unit. Here in Processing-in-DRAM, we don't have that limitation. First, there is no register, so you don't bring data into a register prior to do the computation itself, because the register is the data, is the DRAM cell. So there is no concept of register over there. The second thing is that we have a flexible and very wide SIMD engine over there. So you're not limited to 512 SIMD lanes. You have up to 65,000 SIMD lanes. So that's not the number of SIMD lanes is not a problem. And you can also configure that SIMD lane for different granularities depending on how many DRAM maps you're going to use for computation. So you're modifying that vector units to have in the LLVM compiler to have a notion of these differences between regular vectorizable code for your Intel processor or ARM processor or Processing-in-DRAM instructions. So and since you don't have to load or store data into vector registers, we also remove load and store instructions because again, you don't load and store data. You just access the data because the data is already there in the DRAM chip itself. So that's the first thing that we do. So after you identify those vector instructions and you generate their proper vector code, we need to help the hardware to orchestrate the computation. So to improve utilization. So to do that, we create what is called a data dependence graph of the loops. So this basically is telling me that I have a loop, for example, that does addition of 2 elements, vector addition of 2 elements. and then I have another portion of the loop that does a multiplication, and that multiplication, that addition has no data dependence between them. And then I have a subtraction that has dependence from the multiplication and from the addition, and generates a final output. So what does it mean? It means that I can execute the data independent elements of this graph at the same time in different DRAM mats, because there's no dependence between them, while the operation in that is a node with edges from other nodes have dependence between them. So in the subtraction here, I need to execute after the multiplication in the subtraction. And if I decided to execute the addition and subtraction, the addition and the multiplication in different DRAM subarray, in different DRAM mats, I need to move the data from one of them to the same DRAM, to a given DRAM mat, so they are localized, and I can execute that data dependent operation. So basically, we annotate those instructions with labels that are going to be used by the hardware itself to know that, oh, this instruction here, I can execute as I want. This not in any given DRAM mat based on the vectorization that was identified previously. The next instruction has no dependence from the instruction that I'm executing right now. So again, I can execute them whatever I want in DRAM subarray. The follow-up instruction that I'm executing, I need to wait for the two previous ones to finish because they have data dependence. So I need to maintain order over here. And not only that, I need to move the data from one of the DRAM mats to one single DRAM mat prior to that, because the data was not localized anymore. So this is why the metadata is used. And then finally, there is a back end in the compiler that generates the code, and then we append them with ping instructions over there, so the hardware can execute the instructions. So hopefully that was more or less clear for people that didn't take any compiler class before. But I'm a CS major myself. I highly recommend everyone to take a compiler class. It's so much fun. Anyway, so hopefully that gives you an intuition about what is possible related to system ease of programmability. Then I'm going to talk about system, some other issues with coherence and virtual memory. And then we are going to take a break. So first issue is how to enable virtual memory. So we have different solutions depending on different pin systems. But does everyone here knows what is virtual memory? Or does anyone does not know what is virtual memory? Don't be afraid of saying, otherwise whatever I say next makes no sense. So in a high level, virtual memory enables the programmer to have an intuition that the memory is infinite. And then later on, there is a translation that happens in the hardware, on the operating system together with the hardware, to tell for a given address in your application, this data is located in a particular location inside your real physical memory. So that is this translation that happens in the unit that's it's called page table, together with a memory management unit, which is a hardware unit that is in your processor. The problem with PIM and virtual memory is that if you are executing a graph application, right, inside this 3D stack memory with thousands of PIM chips, and then you are using virtual address space. So the address of a pointer is not the address of a pointer. You need to go and figure out the real address of this pointer by accessing this page table. However, this page table can be quite large, and keeps getting updated. So now you need to distribute this page table across many different PIN cores, and there is a likelihood that the address of that page that you just generated is not even inside that PIN core itself. Might be in another PIN core, because the translation is dynamic. It's going to depend on how you access the data, the translation between virtual and physical address. So this is the main problem of PIM and virtual memory, is that a pointer is not a pointer anymore. I need to figure out the address of this pointer. And figuring out the address of this pointer potentially creates more data movement. And the entire thing that I want to do is to mitigate data movement. So it goes against the problem. But at the same time, if I don't enable virtual memory, programming the hardware becomes way more complicated. It's similar to what the MMP system is doing, because now I have to have a more clear view of how to manage my physical memory itself, which can be quite complicated, especially for irregular applications like pointer chasing and graph processing. But anyway, I'm going to go back to Memory-DRAM because the problem of data allocation and virtual memory becomes even more complicated if your memory is your compute engine at the same time, and if your position of your data dictates where you're going to do the computation. So what's the problem here? So how much background I should give about this? I'm going to take a little bit of time on this because otherwise nothing makes sense. So the way that it works in your system, in your operating system right now, is your application requests memory. So you do a malloc, and your application requests pages of memory. This operation, the operating system then gives a virtual page, so an address that does not have a counterpart in the real physical address space yet. So it's just a physical abstract address for the particular memory request that your application did. Then your memory allocator, which is part of the operating system, maps that particular abstract virtual memory into what is called a frame. A frame is not necessarily a location inside your DRAM chip or your memory itself, but the frame is bounded by the size of your address space. Just means that eventually that data is going to be concrete. So I have the frame. If you have 128 gigabytes of data in your DRAM, you're going to have 128 gigabytes of frames. It's not exactly like that. I'm oversimplifying inside the DRAM chip itself. While your virtual address space might be much larger, but it might be, at some point that frame is going to become a real address inside the DRAM chip itself. Then we have what's called DRAM interleaving. So the way that the DRAM is organized, as you probably know by now, is that you organize the DRAM in multiple banks, multiple ranks, multiple channels, subarrays, maps, so on and so forth, rows and columns, right? There is a mapping that is not necessarily linear between the address of the physical frame and the actual DRAM row that that particular frame is going to be placed. So it does not mean that if my frame at frame 0 is going to be placed in DRAM bank 0, at row 0, at rank 0, banks channel 0, so on and so forth. That mapping is usually based on some hash functions, which are proprietary of the DRAM chip itself. So depending on the realization of your memory controller and the DRAM type that you have, that mapping might change. So this is all to show that there are many levels of translation that request that your application did in the beginning goes through until it gets to DRAM. But we keep talking that we are operating on DRAM rows as if we know from the application perspective where the row is located, but I don't know. That row is the address of the row is going to depend on all of these factors or all of these translation levels that I mentioned over here. So if you do a malloc of your application, so you have many DRAM pages, the memory allocator does the allocation. It gives you some DRAM frames. There is no guarantee of boundary, so you don't know if that allocation is going to be bound by a cache line, by a row, or by any other type of alignment. The same for the frames. You don't know if the frames are going to be contiguous in the address space. So there's no guarantee of alignment. And same to the DRAM row. You might be the case that one frame is placed in one row in one bank, then the next consecutive frame is placed in 5 banks from that one, and the other one in another bank, on a different bank, completely different from the previous 2. So basically, this is the worst case that can happen. So here we have no control whatsoever of the allocation. Then there are families of allocations inside C++ that guarantee that pages are going to be aligned over some boundaries. So this is good. So now you can at least have some alignment in the virtual address space. But again, this does not guarantee to us that the frames are going to be aligned, neither that the rows are going to be aligned inside the DRAM bank. Finally, there is another way, there is another family of allocation that's in your operating system that are called huge pages. So those huge pages are sets of, for example, 2 megabytes of pages. A regular page is around 4 kilobytes usually in the operating system. And the huge pages, those pages are around 2 megabytes each. And in those pages, the operating system guarantees to you that the pages are going to be aligned, and the memory allocator guarantees to you that the 4 kilobyte pages inside those 2 megabyte huge pages are going to be aligned inside the physical address space. So the frames are aligned. But still, I have no guarantee that those physical frames are going to be aligned in the inside the DRAM row. So still, the rows can be mapped, the frames can be back inside the DRAM row, completely dependent on the operating system based allocator. So this is the worst case. So now it means that I create all of this system to do process using DRAM computation, but I cannot even guarantee that my data is going to be placed as I need it. So if I do A plus B, I don't know where is A, I don't know where is B. Hopefully I add the two together, generate C, I don't know where is C as well. So I can do the computation, but I don't have a way to control it. So this is the problem. So solving this problem requires a new allocator that is that take into account all of those issues that I mentioned over here. And this is what we do in MIM-DRAM, where we are going to combine huge pages. So huge pages is not that bad, right? I still can guarantee that the frames are aligned. The main problem is this DRAM interleaving here that I don't know where the frames are going to end up inside the DRAM chip itself. So basically what I need to do is I need to reverse engineer my DRAM chip to figure out what are the hash functions inside that are used to allocate frames into DRAM rows. And based on that, now, because I can just apply the inverse of that that hash function, and then I can know where a particular frame in a huge page is going to end up inside the DRAM chip. So now I can have knowledge of where a frame is. Based on this knowledge, then I can organize this space over here. And then when application does a pin-based malloc operation, I get the data from those huge pages that fits inside the same DRAM subarray in the same boundaries. Because again, I reverse engineer the hash function. Then I just need to manage that in a way that if I have to do operations over input arrays that need to be placed inside the same DRAM subarray, the allocator keeps track where those data is and map the next dependent data to the same set of DRAM subarrays. That was very complex, but what I'm trying to say here is that if I can do a first allocation here, like let's say that I want to copy a source array to the destination array following row clone. So when for the source array, I can allocate it wherever it fits inside the DRAM chip itself. It's not a problem. The problem is that I need to make sure that when I allocate the destination array, the destination array is inside the same subarray than the source array. The source array was allocated. Otherwise, the copy is not going to be performed correctly, right? Because I need to be inside the same DRAM subarray. So I need to use a different API that takes the source DRAM subarray as a parameter, so that the allocator knows that when I allocate destination, give me an address that fits inside the same DRAM subarray as that, so that I can perform the operation. So this hopefully is more complex than what I just mentioned here, but hopefully gives you an intuition of the problem and how we can hopefully fix the problem with a little bit of more engineering effort. Okay, so this was the memory allocator issue in MIM-DRAM. Is there any question related to this? I talked a lot. reverse engineer. So the way that we do this a lot already in Safari because we need to know where the rows are when you do RowHammer attacks. So basically, what we do is we brute force RowHammer operations, not RowHammer, row clone operations in the substrate on the FPGA based framework that we have. And if the the row clone operation is performed correctly, we know that those rows are in the same DRAM subarray. Otherwise, they are not there. And then based on that, we construct that hash function. But again, it's very brute force approach. There are other ways of doing that. There are other works that tries with different methods based on, for example, excess latency of different portions of our array to regenerate this reverse engineering function. But again, if you are a menu manufacturer, you know that function already. So this is just the case, like if you're coming from CPU vendor point of view, the CPU vendor also know. If you're coming from an outside point of view, that you don't have that information because it's proprietary. But hopefully that designer would know this beforehand. Any other question? So you fully rewrite the kernel or have there is this concept of bare metal, right? That you you don't have like multiple of like virtual memory, all those things. So then, yeah, you don't. That's the problem because this is. I don't think so because this is a property. This is needed because this is a property of the memory controller. So the memory controller knows this information of this interleaving. The operating system does not know because the operating system is just interested on frames. So the operating system just has control until here. From down here is the memory controller that have control over, and it's not programmable from the operating system. Okay. So let's move to coherence. So we are going to have lectures on coherence later on during the semester, but I just want to highlight one problem. So if you have your pin cores, your whole CPU here, and you have your DRAM with some compute engine here that does some computation. Let's say that they both operate over the same kernel at the same time. And they are, of course, they are doing different instructions, but they are operating on the same task at the same time. There will be a time that the pin system might update some data and that the whole system needs to read, but this data is not valid anymore in the cache of the whole system because the pin updated the data. So the pin system needs to send a coherence message to the pin cores to tell the pin core all this data was updated. And then now the whole CPU can access the data and do whatever it needs to be done. And this is going to generate more traffic in the bus just for these coherence messages so that the data is constantly updated in both hosts and the same is true for the other side. So if the CPU updates some piece of data that is in the cache, but this data is also going to be operated by the pin core. Another coherence traffic needs to be sent from the host to the pin cores, generating this communication issue over here. So basically, coherence in this type of distributed execution model from host and pin further exacerbates data movement bottlenecks. So again, we are going against what we are trying to mitigate in the beginning. And of course, there are different coherence protocols available in the systems today, and we are going to study them later on. But they are not. They just exacerbate this issue. The main takeaway that I'm going to use this model here is a lot to just say. Okay, this is much easier to understand. So what we are going to do is is an optimistic execution. So you are executing that kernel in the CPU, and then you're going to offload the computation and execute that computation in the pin system. And we are going to forget about those coherence messages. So if the pin system updates invalid data that was updated by the CPU, it's okay for now. Then you're going to have some checkpoint areas that you're going to store every single write access that the pin system generated during that particular piece of execution of code. And then when you reach to that sequence of instructions, to that checkpoint mark, we send that bitmap with the addresses that the pin system wrote to the pin. We call that signature to the pin core, to the whole CPU, and then the whole CPU see if there is any write operation that it also performed during that epoch of computation. If that is the case, it means that the pin unit executed over invalid data. So that computation is to re-execute again. So, but we see that most of the time, the CPU and the pin cores execute over this joint piece of data. So most of the time, you don't have to re-execute that piece of code that the whole CPU, the pin cores just executed. So then you're not doing a coherence request every time that you access data, just at the end of the epoch, sending those signatures just for writes. So then you remove that coherence traffic that was required earlier on. Of course, that is the clear drawback that we have here is that in the case that there is a match between those signatures, we are going to have to recompute. But the main premises here is that that's not going to be the often case. Yeah, so either you commit so there was no issue, or you re-execute the computation. So we evaluate this, and we see that compared to this is fine-grained based coherence model, which you're going to learn during the end of the semester. We can significantly reduce coherence traffic and improve performance with this approach. I'm going to get into detail over here. So finally, synchronization. We have created some API-based synchronizations for UpMem-like system using Synchron, which I'm not going to get into detail here because of time. So is there any question related to all of this? Okay, so we are almost done. Let's take a 10-minute break, and then we finish up on the runtime for pin systems. Okay, let's try to finish without me going over time. So now we know how to identify if application is going to be suitable for process memory. We know how to program this application, rewrite this application, and deploy this application at low programming effort. We know how to execute this application and make sure that you can guarantee virtual memory support and coherence. Now you're going to look at how we can make use of data properties to have more efficiency when you're doing computation. So one example that I'm going to do is for process using DRAM. So process using DRAM systems, they suffer from 3 issues, which I'm going to build on next. But before, I want to give a little bit of refreshment on how you do arithmetic operations inside the DRAM chip itself. So let's say that you want to do an addition operation of 2 vectors, vector A and vector B. Each one of those vectors have multiple elements. Each element is stored in one of the DRAM columns in the DRAM subarray, but each element is only 1 bit. So you're going to add this entire array, A, B, and here blue means 1 and yellow means 0. So you're going to build, add 1 plus 1, and you're going to have 2 in the end. So how you do that, following the SIMD-DRAM framework, the first thing is that we get implementation of a adder. So here we have a RIP carry adder, and then we translate this circuit that has Boolean gates to a circuit that only has majority and not gates, because this is exactly what you do when you do multiple activations inside the DRAM subarray. Then we traverse this graph node by node, issuing the triple row activations and realizing the addition operations as we go. So first, we go to the first node that does the majority of A, B, and carry in. So you're going to have the majority of A, 1, 1, and 0, which is going to be 1. It's majority of 3. And this data is going to be stored on this carry out row over here. Then we move to the next one, which I didn't animate, but then finally we move, it's going to give 0, and it's going to be, and then in the end, we do the majority of the previous 2 majority gates. The first one was 1, but we negated it. And the next one was, I hope you believe in me, was 0. So it's going to be 0, 0, and 1, which is going to be 0. And the end is going to be stored in this sum row here. And then in the way that we read this is in a vertical way. So we combine the data stored in the sum row together with the data combined in this carry out row, the other way around. So carry out first and then sum. Then you're going to have 1 and 0, which is 2. So then we have the output of that addition operation. So if you want to do this operation over 32 bits, we repeat this process that I just mentioned 32 times. So if you want to do this operation of data that is 64-bit, repeat this 64 times, so on and so forth. So basically, when you do computation like this, we transform the RAM subarray into a bit serial SIMD engine, as I mentioned earlier. But the very important word here that I want to highlight is bit serial. So you operate bit by bit. So there is this phenomena that is known in the literature that's called narrow values. So when you're writing C code or C++ code, and you are instantiating an array, do you often think about what are going to be the maximum and minimum values that are going to be stored in this array? Is that a question for you? You just use, I don't know, integer, because why not? Usually is the case, right? You just use whatever format that you believe that those elements are going to take, but you don't worry much about the range of those values, right? So it does not matter for you if my array or my integer is going to take the maximum value of 4, which only requires 2 bits and a sign, or if it's going to take the maximum value that an integer with 32 bits is going to take, right? And usually it's fine, but this creates this problem called narrow values, which is called, the problem is that dynamic data with that small dynamic range is often stored in large data format. So here we have example, we have A that's going to be stored into an integer, not an integer, 8-bit element, like a char, for example. So if I'm storing 4 over there, the 3 least significant bits are going to have the data that I want to store, 4. But all of the other most significant bits are only going to store zeros. In systems, this generates different problems. Like, for example, you are storing a bunch of zeros in your caches, so you're wasting space of your cache for nothing. And there is a lot of compression work that propose compression mechanisms in your cache to reduce those zeros over there. But here you're going to see that this creates another problem. So for example, if I want to do addition of A and B, A has 4, B has 2. I only need those 2 least significant bits, and the sum is going to be 6. So I only again need 3 of the least significant bits. If I do this operation in the bit serial manner in DRAM, as I mentioned earlier, I'm going to operate in a lot of what we call inconsequential bits. Those are those most significant bits over here. There's just store zeros. So I need to do those triple row activations that I just mentioned in the background, also inside for each one of those bits over here in my input array or my input data. This is going to create a problem because as I increase the bit precision of the computation, the latency and the energy that it takes to do that bit zero operation is also going to increase. And I'm going to be wasting a lot of latency, a lot of energy on those consequential bits for the bit zero operation. So how first is this a real problem? So we went to a bunch of real applications and we tried to classify what is the required bit precision for those applications. So you're actually looking at the values inside those arrays and seeing what is the maximum and minimum value that actually those arrays are taking. And then we store actually the maximum, and we are storing them into those box plots here that show the distribution of those bit precisions and also the larger and smaller bits. So what you can see here in this plot is that first, the amount of narrow values inside those applications significantly varies. So in a lot of applications, you don't even need those 32 bits. Actually, most of them you don't need 32 bits. And in some cases, you need only, I don't know, 8 bits, even though you are storing the data in 32-bit arrays. And this is, again, a property of the application, how the application is written. So this is a real problem. This is just one to highlight. So our way of solving this problem for our bit precision, for our process using DRAM engine is, if I know before the execution that the maximum value that this array A is going to take is 4, and the maximum value that array B is taking is 2, I know for a fact that the maximum possible output for the operation is going to be log of the maximum of A and the maximum of B. So maximum of A is in this case here 4, maximum of B is 2, A plus B is 6. So the maximum number of bits that I'm going to need is log of 2 of 6, which is 3 bits. So if I can know prior to the computation that the maximum possible value that this array, that computation is going to take is 3 bits, I can ignore the remaining 5 bits here when I'm issuing those triple row activations to the DRAM chip. Then I can terminate the computation earlier, and you can reduce the latency and the energy of the processing using DRAM operation. So this is the first idea. Then you have another idea, another problem. So even if you identify that narrow values, still, if you have a lot of bit precision that you need to go through, so you have multiple bits that you need to operate on top of. If you have arithmetic operation, you're going to end up having this interbit dependency here. This, you can think about this as a carry propagation in an adder, but it's the same for subtraction. It's worse for multiplication, and even worse for division. So in a bit serial operation, the operation of the one bit depends on the computation performed from the previous bits. So there is this serialization nature of the computation over here, which generates creates the latency problems. So here now again at the same problem, now you have A and B story. Each one of them have 2 bits, and all of the data is stored in a single DRAM subarray. So here I'm doing I have the DRAM cycles that I do the triple row activations, and as you can see, I do the activation first for the majority operations first for the first bits, so bit zeros. Then the carry is generated, this interbit dependence, and then I need to do the triple activations for the other bits here, bit 1 in this example for the addition in a serial manner. So there's no parallelization. So, but if you look at the circuit here, forget about this interbit dependence. You can see that if I fix this interbit dependence, or if I can, once I propagate the carry, I have a lot of majority gates here in the circuit that actually are independent of each other once I figure out the interbit dependence. So we call that interbit independence, of course. So the main problem is that for us to leverage this interbit dependence, I'm operating the single DRAM subarray before, right? So all of my bits here, A and B, they have 2 bits each, are in a single DRAM subarray. So even if I have that parallelism available, I'm bound by this sense amplifier over here, which is only one sense amplifier inside the same DRAM subarray. But there are multiple DRAM subarrays in a bank, so there is no reason for me to be restricted to only one. So I can actually distribute the bits of my value. So now I have bits 0 of array A and B stored in subarray 0, and bits 1 of subarray of our elements A and B stored in subarray 1. And if I have a way of quickly propagating that carry that is generated from bit 0 to bit 1 using some sort of inter-subarray interconnect, I can execute those independent majority gates here at the same time once that carry propagation was solved. So this is exactly what we are going to do. So you compute, we start again generating that first majority gate here for bit 0 in subarray 0, which generates the carry out bit that is going to be needed for bit 1 computation. Then I use this fast interconnects to copy the data from subarray 0 to subarray 1. And then now everything becomes independent of each other. Because as I mentioned, those other majority gates are data independent from each other. So I can execute them at the same time in those 2 DRAM subarrays, hence saving some DRAM cycles for the computation itself. So is this more or less clear how it's operating? Okay, great. So still there's another problem. Even if I can leverage this parallelism, even if I can reduce the computation using those narrow values, there is an extreme case that there is no narrow value, so I need to go through very high precisions here. And if I need to go to very high precisions, I'm going to even though I'm reducing that I'm solving that interbit dependency, still there is some serialization that happens in the beginning of the computation. So in this one over here. So if I have high bit precision, this is just going to be accumulating over the bit precision of the computation. So, and this is even more problematic for what we call quadratic scaling process using DRAM operations. So the way that you do multiplication is by doing multiple adding operations and shifting. So you add and shift, add and shift, add and shift. So this means that the latency is going to scale quadratically with the bit precision of your computation itself, and also the energy. So in that case, neither of the solutions that I just mentioned before are going to be actually beneficial over here, because you don't have narrow values to explore, nor you have parallelism to extract, or the parallelism that you have to extract is not enough to hide the latency of this quadratic scaling computation. And this is a problem because of the data format that we're using. So you are using this binary system that operates propagating carries bit by bit. And this is a natural effect on how the data representation format that we are using to complement in a bit serial manner produces. So what you need to do is to shift away from this Boolean representation of two's complement representation of data to a different data format, which you are going to call it's in the literature actually, it's nothing new. Redundant binary representation. So here you're not going to use only 1 bit to represent 0 and 1. We are going to use 2 bits, which can take any value between -1, 0, and 1. So here, example, how we represent the number of 3. We represent that using 0, 1, 0, -1. So, and then is again a position-based system. So 0 times 2 to the 3 is 0, 1 plus 2 to the 4 is 4. And then -1 times 2 to the 0, which is 1, gives 4 minus 1, which is 3, which represents the data that you need. So this is a representation, data representation format that exists over there. People uses this a lot in VLSI circuits. So what you're going to, and one property that this representation format provides is, since we are using multiple bits to represent one single value, it's not only one bit anymore. This creates redundancy. This is where the redundancy comes here, and this redundancy in the format allow this arithmetic-based circuit to use in this format to be latency independence, because the carry is going to be limited to at most 2 bit positions at a time. There is a math that explains why, which I'm not going to explain over here. I hope you just believe that this is the case. And what this means is, if I have a operation that I need to execute in the DRAM chip that have high bit precision and is quadratic in nature, instead of using that computation, doing that operation using 2's complement, I'm going to convert that input data to this redundant binary representation. Then I do my operation, which is going to be latent independence, and then I convert it back as needed. Of course, the conversion and has a latency by itself, but in some cases is more beneficial. So, okay. So based on all of these ideas, we propose this framework called Proteus, which is a runtime framework composed of 3 main components: a parallelism-aware microprogram library, a dynamic bit precision engine, and a microprogram selection unit. So how this works? So first, offline, we implement different versions of what we call a microprogram. Microprogram is just a sequence of in-DRAM activations that implements our target operation. So think about that carry adder that I mentioned in the beginning. So there is different ways to implement an adder, right, with different latencies. So you can be a constant adder, I forgot the name, but there are many other types of. It's going to come to me later. All type of implementation of various circuits, bit serial or bit parallel. And the most important thing is that those implementations have different latencies in terms of the target bit precision. So if you have like a small bit precision, maybe it's better to just do a RIP carry adder, but if your bit precision increases, maybe it's better to do a bit parallel adder, for example. And then we save this in this microprogram select unit. Then the important thing is this dynamic bit precision engine, because the entire idea depends on us being able to identify what is the target bit precision that you're going to need to execute in the system. And we do that by probing the data that is being evicted to the DRAM chip prior to the process using DRAM execution, and storing in some SRAM array what is the maximum value in the arrays that we have encountered so far. Note that here I'm not interested in all of the values. I don't need to store all of the values of the input array, because as I mentioned earlier, it's enough for me to know what is the maximum possible values in that array, so I can calculate what's the upper limit of the target bit precision. Of course, if I want to be more precise, I could calculate the upper and the lower limit, but then it will require more space inside the chip itself, which is not useful. So now, by doing that, I know what is the maximum possible elements in different arrays that are going to be used for computation later on. Once I know that, when I trigger a process using the DRAM operation, before doing that, I can calculate with exactly what I mentioned before, what is going to be the upper bit precision required for that particular computation. So in this case, if I do addition between A and B, I know that the maximum addition is going to be a maximum between 7 and 9, which is 16, which if I take the log of that, I know that I require only 4 bits to generate the output for. So the maximum target bit precision that I'm going to need for that particular addition operation is going to be 4. So I can ignore all of the other bits doing the computation. Then we probe the microprogram, the parallelism aware microprogram, to identify what is the best performing sequence of in-DRAM operations that does the computation based on that bit precision. And then I issue that computation. So is there any question related to any of this? Hopefully it's more or less clear. Everything here is in hardware. This is a good question, I didn't explain. So all of this is sitting between the last level cache and the memory controller over there. Okay. So we evaluate all of this in simulation, and the important thing that I'm going to show here, that this is performance for those 12 applications, is that most important thing here is if you take SIM-DRAM, which is the green here, the green bars, this is just using the static bit precision, the stored 2-bit elements, without taking into account narrow value. And then you can see that even sometimes we lost performance compared to the CPU over here. But by leveraging data information about the data and skipping those narrow values in Proteus, we can significantly gain performance compared to SIM-DRAM based execution. Because again, we are avoiding doing triple row activations on top of inconsequential value, on top of zeros. This is the most important thing. And of course, this also translates to energy. So this is Proteus. Is there any question related to this? So maybe this is just for you to highlight to you that you can always further optimize your system if you understand better which data that is going to be running that particular application. And this is not only true for processing memory, but as I mentioned, for cache management is also very important, where you can do compression based on this type of insights about the data. Okay. So finally, Onur already mentioned all of this. The last thing is that you need to be able to test those ideas, right? And see quickly if you can get benefit from processing memory systems. And that require infrastructure for you to test. So we do a lot of studies in Safari using FPGA-based infrastructure that was already mentioned here. The initial implementation was called SoftMC, which has this FPGA that allows us to have control over the runtime parameters of the DRAM chip. And we have a new realization called DRAM Bender, which further extends SoftMC. Other approaches like the DAMOV simulator that I mentioned here earlier is also one tool that allows you to do research on this, and also Remulator itself. And all of this is available in your GitHub. There's a bunch of different simulators there if you want to just test them. And probably you're going to be playing with at least Remulator during the semester, if I'm not mistaken, for some of the projects. So, okay, so to conclude, you probably already saw these slides here. Is there any question from what I just mentioned before? Okay, great. That there is an opportunity right now for us to design more energy efficient and more high performance systems that minimally move data with processing memory. To do that, there is still a long path to solve. So as I mentioned, as I went through those works over here, we had an idea of the problems that are out there, and not only the problems that are out there, also that those solutions are not bulletproofs. I try to highlight some of the weakness of the solutions. So you have the idea that we still need to do more. So we have to have more research that needs to be conducted for us to have more a more efficient system adoption solutions for process memory applications. So there is still a lot that needs to be done. But the future is very bright, especially because now you're seeing a huge push from industry to make those architectures more and more commercially available in current and future systems, which is very good, particularly for me because I'm getting a job soon. So I need to earn money with all of this knowledge somehow. So I guess this concludes the talk. I thought that if going too fast. And if you want to just read more about process memory, we have this pink book chapter that summarizes all of those issues that I mentioned earlier. Yeah. So if there's no other question, we're going to end up a little bit earlier today. So thank you very much for your attention and have a good weekend.